Picture this. You wake up one morning and discover that the single largest technology investment in human history, over $1 trillion currently being funneled into massive AI data centers, could become completely worthless. Not decades from now, possibly within this decade. That is not a plot from a science fiction thriller. That is an actual conversation taking place right now inside the most powerful companies on the planet. And the force behind this potential collapse is not a new AI model, not a faster chip, and not a software breakthrough. It is quantum computing, a technology so fundamentally different from anything we have built before that researchers are still searching for adequate language to describe it. And in 2026, it is starting to do something nobody expected this early. It is beginning to undermine the AI data center industry as we know it. To grasp why this matters so much, you first need to understand the sheer scale of the AI data center explosion. This is not a story about server rooms getting a hardware refresh. This is one of the most expensive infrastructure build-outs in the history of civilization. In 2025 alone, the world spent an estimated $580 billion on AI-focused data center infrastructure. Microsoft committed over $80 billion in capital expenditures for fiscal year 2026. Meta projected spending between $80 and $100 billion in the same year. Google, Amazon, and every major hyperscaler on Earth is sprinting to build the largest, most powerful AI computing facilities that money can buy, and the ripple effects go far beyond tech. Us utilities alone are planning $1.4 trillion in spending just to supply power to these facilities. Electricity prices for American households have already climbed nearly 40% since 2021, driven largely by this surging demand. And some estimates suggest consumers could absorb as much as $700 billion of that utility spend through rate increases. If you have been wondering why your electricity bill keeps going up, that is a big part of the answer. The energy problem tied to AI data centers has moved well beyond economics and into crisis territory. The International Energy Agency now projects that global data center electricity consumption will surpass 1,000 terawatts hours by the end of 2026, the equivalent of Japan's entire annual electricity usage consumed solely by data centers. The World Economic Forum has forecast that data center energy use will double between 2024 and 2027. In Ireland, data centers already account for 21% of total national electricity consumption, a figure expected to reach 32% by 2026. In the United States, total data center energy demand is projected to nearly double, from 80 gigawatts in 2025 to 150 gigawatts by 2028. And this explosive demand is colliding with a power grid that simply cannot keep pace. Grid interconnection queues in major utility territories now stretch 3 to 7 years. Data center cancellations due to community opposition quadrupled in 2025, with at least 25 major projects scrapped outright. Maine became the first U.S. state to impose a full moratorium on large data center construction. The AI industry built something it cannot fully power, and that something is now straining grids across the developed world. So where does quantum computing enter this picture? At the most fundamental level, because the core problem with how AI works today comes down to the limitations of classical computing. Every AI interaction you have ever had, every chatbot response, every generated image, every AI-assisted recommendation runs on classical hardware. Classical computers process information in bits, and every bit is either a 0 or a 1. That binary simplicity is reliable, but at the scale modern AI demands, it is brutally energy intensive. Training a single large AI model can consume as much electricity as 5 average American homes use across their entire and lifetimes, and running that model after training, what engineers call inference, happens billions of times daily, drawing enormous amounts of power around the clock every single day of the year. Quantum computers operate by entirely different rules. Instead of bits, they use qubits, and qubits can exist as a 0, a 1, or both at the same time, a property called superposition. Qubits can also become entangled, meaning the state of one can instantly affect another regardless of distance. Together, these properties allow a quantum computer to evaluate an enormous number of possible solutions simultaneously. Rather than working through them one at a time the way classical machines do, an UBS analyst report from early 2026 described how the industry is approaching a quantum computer capable of solving a specific problem in just 200 seconds, a problem that would take a conventional supercomputer 10,000 years. That is not a marginal improvement. That is a categorically different kind of machine. In 2026, the leading quantum computing players have each crossed milestones that were considered theoretical. Just 2 years ago, Google demonstrated the first verifiable quantum advantage with its Willow chip, running a specific algorithm 13,000 times faster than classical supercomputers. IBM unveiled processors pushing past 1,000 qubits. Microsoft made substantial progress with its topological qubits architecture, which is designed to resist errors without the complex correction systems that have historically slowed quantum development. Microsoft's Majorana chip, built on a breakthrough class of materials called a topoconductor, has been described by experts as a transformative step toward practical quantum computing. These are not marketing announcements. These are real engineering milestones produced in real laboratories. The specific threat this poses to AI data centers comes down to one word: optimization. The overwhelming majority of what AI data centers actually do is find the best solution among billions of possible options. Training a neural network is an optimization problem. So are fraud detection, drug discovery simulations, logistics calculations, and content recommendation engines. And optimization is precisely the category of problem where quantum computing delivers its most dramatic advantages. Quantum systems are already beginning to handle optimization tasks in minutes or hours that would take classical supercomputers days or weeks. When quantum hardware can do this reliably and at scale, the need for hundreds of thousands of classical GPU servers drops significantly. The energy equation changes, the infrastructure equation changes, and the trillion-dollar bet sitting inside those sprawling classical computing facilities starts to look like a very different kind of investment. This disruption does not require quantum computers to completely replace classical systems overnight. The economic damage begins the moment a credible timeline for practical quantum advantage becomes widely accepted. Many experts now place that timeline between 2028 and 2030 for fault-tolerant, commercially viable quantum systems. At that point, the logic of pouring billions into new classical GPU data centers starts to break down. Why would any company spend $5 billion on a new classical facility in 2026 if credible quantum hardware is expected to be commercially available within 3 to 4 years? Capital flows shift before the technology even arrives. Google's CEO Sundar Pichai has publicly stated that practical quantum workloads could emerge within 5 years. That is a market signal, not a casual remark. The energy dimension of this story may be the most powerful driver of all. Classical AI data centers do not simply use electricity. They consume it at a scale that is reshaping national energy infrastructure. Quantum processors themselves use relatively little energy during computation. The energy-intensive element of quantum systems is the cryogenic cooling required to keep qubits operating at temperatures colder than outer space. But even accounting for that, a single quantum processor performing millions of simultaneous calculations uses a fraction of the energy that hundreds of thousands of classical processors would need to attempt the same work sequentially. The most realistic near-term promise of quantum computing is not to eliminate data centers entirely. but to dramatically reduce the energy and physical footprint required per unit of AI work performed. In a world where AI energy demand already rivals the electricity consumption of entire nations, that efficiency shift is not a technical footnote, it is an economic and environmental necessity. There is also a security dimension that is being discussed with increasing urgency across governments and financial institutions. Quantum computers, as they grow more capable, will be able to break the encryption standards that currently protect every piece of sensitive data stored inside AI data centers. The mathematical problems that make today's encryption effectively uncrackable for classical machines are precisely the kind of problems quantum systems are built to solve. The cybersecurity community refers to the moment when this becomes possible as Q-Day. International standards bodies are already developing quantum-safe security frameworks, and major enterprises are being advised that quantum-resistant protocols will be essential by 2030. Data centers built today will need to be substantially retrofitted to function securely in a post-quantum environment. That is another layer of disruption and another reason the current model is operating on a compressed timeline. The disagreement at the top of the industry has been striking. At CES 2025, NVIDIA CEO Jensen Huang stated that practical quantum computers were still 15 to 30 years away and that classical GPU-accelerated systems would remain dominant for the foreseeable future. And quantum computing stocks dropped sharply in response. Less than a year later, Microsoft, Google, and IBM had each delivered breakthroughs that directly contradicted that timeline. And by 2026, even the most skeptical voices in the industry have been forced to revise their positions. NVIDIA itself launched a family of open-source AI models called Ising, built specifically to address the error correction. Challenges that have long been quantum computing's biggest obstacle, even the leading skeptic is hedging. What this means in practical terms is that the future of computing is not 10,000 GPU data centers consuming more electricity than Japan. It is a hybrid architecture in which quantum processors handle the most complex optimization and simulation workloads, while classical systems manage data storage, routine inference, and everyday operations. The center of gravity is shifting. Companies and governments that recognize this now and begin positioning accordingly will soon be the ones that define the next decade of technology. Those that continue pouring capital into classical infrastructure without accounting for quantum disruption are making a wager that history may not treat kindly. For ordinary people, the stakes in this story are more direct than most technology coverage ever acknowledges. The AI data center boom is being partially funded by residential consumers through rising electricity bills and utility rates. Increases. Goldman Sachs has warned that data center-driven electricity demand will push core inflation higher through 2028, when quantum computing begins delivering comparable or greater AI capability at a fraction of the energy cost. And that will not just benefit shareholders, it will take pressure off power grids, slow the rise of electricity prices, and provide real relief to millions of households that have been quietly subsidizing a technological revolution without ever being asked. The trillion-dollar question is not whether quantum computing will disrupt AI data centers. It is how fast every credible projection now places commercial quantum advantage within the next 3 to 5 years. Every major technology company is investing heavily in quantum. Every government with serious technology ambitions has a national quantum strategy in place, and every data center being built today on classical computing assumptions is either going to evolve or be left behind. What is unfolding right now in 2026 is the opening chapter of the most consequential technology transition since the invention of the Internet. Quantum computing did not deliver a single decisive blow to the AI data center industry. It started something slower, deeper, and ultimately far more complete, a disruption so fundamental that many in the industry may not fully understand what happened until the transformation is already over.